All right, we might make a start. Thank you very much, everyone, for joining us here, and to everyone who's watching on the webinar. I hope everything's working okay online. Today, I'm Claire Brownridge from the Climate Change Policy area of the Department of Environment, Land, Water and Planning. And today we've got John Clark from CSIRO, who's going to give us an update on the project that we've been working on to produce Victorian Climate Projections 2019. So these have been new updated projections and a whole host of data and analysis associated with those that will be available early 2019. John will give a bit of a background and introduction to the project. I think a few people, it might be new information. Then talk a bit about progress, deliverables that will come out, and products that will come out at the end of the project, and then talk briefly about some of the preliminary results that we've seen so far from the modelling. So I'll hand over to John, and thank you very much.
Thanks, Claire. So yes, I'm John Clark, and you can see the names of the team members from CSIRO who are working on this particular project. It's a lot of work, but it's going to be really good outcomes. So jumping into, whoops, okay. Why is this not working? Here we go. We're good. All right. So just quickly, what I'll talk about, as Claire said, a brief background, progress to date, what we're actually going to be delivering at the end of the project or throughout, and yeah, an early, very brief look at the results, which unfortunately I'm unable to leave with you. I have to keep them embargoed for the time being. So for now, let's look at the background just really briefly. So fairly obviously, the project is a DELP CSIRO project, and what we're actually delivering are stakeholder needs assessment, which has been completed, scoping report, which has been completed, new 5-kilometre resolution dynamically downscaled datasets, which I'll talk about in a little more detail, and a package of projections to suit stakeholder needs that draws on all available data sources, not just the new modelling, and a suite of evaluated or ready-to-use datasets as well, a bunch of guidance material to explain how to use it all, and some communication products, training and outreach. We've got to get all of that done by the end of March. But just to set a bit of background context, let's give you a little bit about the way in which we do this stuff. So climate models are the fundamental tools we use to develop an understanding of plausible future climates, and with that come data sets. But there's a whole bunch of different types of modelling. There are statistical methods, there are dynamical methods, and a whole bunch of different resolutions. But they're basically models, and we all know all models are wrong, but some of them are useful. And because I'm a scientist, there's a caveat there. They're only wrong in some ways. But it's important to know the nature of the wrongness, if that makes sense, so that you can figure out how best to make use of the information they do provide. So the new modelling we'll be doing, let's just start talking about that. It's using CSIRO's CCAN model, which I'll talk about a little bit more. But essentially, the idea with downscaling like this is to reinterpret what the global climate models tell us. Global climate models have a very large grid size. Downscaling is a way of reducing that grid size, but they take information from the global climate models to start with. And typically there's two different ways you can do this. You can use a statistical approach, or you can use a dynamical approach, or what are usually called regional climate models. Now, what you have to get out of downscaling is that because these finer resolution models can resolve topography better, you hope that the modelling will give you a better realisation of what the climate may do in response to topography. It's also better for resolving some of the weather phenomena that happen at smaller scales, smaller spatial scales, like storm events, strong convective processes, tornadoes, those kinds of things. And also at time scales, so things that happen at short time intervals. There's the potential for dynamical downscaling to represent those better. They're also good at simulating urban features and coastal features, and there's potential for them to reduce some types of errors from GCMs, and potential for them to take more detail into account with land use. Now, a lot of that just comes by virtue of the fact that it's finite resolution. The CCAM model, as it's called for short, stands for Conformal Cubic Atmospheric Model, is a particular type of regional climate model called a stretched grid model. And in this case, you can see that if you look at the little diagram in the top right, we've got a cube, and that cube's divided up into grids. But then if you project that cube onto a sphere, that's where you get this cubic conformal atmospheric model approach. So you have a grid that's stretched across the whole globe. Then you can define the grid spacing that you're interested in having over your area of interest and make them as small as you like, pretty much. The reason it's called a stretched grid is that you have this fine resolution over your area of interest, and then the grids get larger as you move away from that location. So by the time you get around to the opposite side of the globe, you've got a very large grid size. There are lots of advantages to this approach. The biggest one is that there is no edge. Some of the other dynamical methods and some of the statistical methods have a defined square region or a rectangular region, and they have inputs from the global climate models fed in around the edges. And there are a whole bunch of issues that can be created through that method. This approach gets around that. The information that CCAM takes from the global climate models is just the sea surface temperature. So you take the sea surface temperature from global climate models, and then CCAM creates its own atmosphere using that as the input, and then it checks in on those sea surface temperatures every now and then and resets and keeps simulating. So the difference between global models and regional models is fundamentally about grid size, but it's good to consider them both. You need to look across the range of the outputs from all of your global climate models and all of your regional climate models. I'll talk about that in a bit more detail shortly. And crucially, you must evaluate the results from those models. You can't just take it as a given that the modelling will be as good as it can be. And you also can't take it as a given that just because you've got a model that's running at a high resolution, that it will give you better results. It's important to look at them and make sure you see where their strengths and weaknesses are. I just want to show you one example of where the CCAM model has been used to develop some projections for urban areas. And I'm only going to look at this really briefly, but just basically to show you that in that bottom panel, you can see how the model has reproduced the urban heat island effect in Melbourne really successfully. So just to highlight the fact that with this higher resolution, hoping to get these finer resolution types of details that you just can't get from a global climate model. But taking a step back again, CCAM is one set of results, but there's also a whole bunch of others out there. And when we first started to talk about this project, initially we were talking about just doing the CCAM modelling for Victoria. And we said, well, hang on, there's a whole bunch of existing data out there already. We hear from stakeholders all the time that it's confusing, difficulty figuring out which data to use and when. So we thought, okay, what's needed here is a bit more than just producing some new modelling. Then in addition to the plethora of data sets, there's a whole bunch of misconceptions out there, and here's just a snapshot of some of them, some of which I've already alluded to. My favourite is, I just want to use the best models. The trouble with that is if you get 10 climate scientists in a room and ask them to tell you how to work out which are the best models, you'll get 10 different answers. There's no international consensus on how to do this type of evaluation of models. So best depends on what it is you're measuring. But it is fair to say that some models are not as good as others, and we prefer to take the approach of trying to figure out if there are some models that we shouldn't be using, or if there are some models that we shouldn't be using in certain sets of circumstances. The other one I really like is all models are useless, which you hear from time to time. So yeah, just see what I said above. Also, we very often hear, don't give me a range in the projections, I just need one number. And this is a fundamental problem with future climate. It's a fundamental problem with future anything. If you give me one number for what Australia's population will be like in 2040, I'm not going to believe you, because I don't believe you know what the population will be in 2040. Give me a range. That's because I'm a scientist. If you just take a single number, you run the risk of ignoring some potentially really important future plausible climates. So it's absolutely critical that we don't just work with one number. This raises the very real possibility that you could invest a lot of money in maladaptation if we just pick a number and we've picked it for the wrong reasons, or we've just been unlucky. And finally, I'll just talk about the high resolution is better question, which I've already mentioned. I keep saying higher resolution modelling has the potential to add value to climate projections, and often it does, but it doesn't always. So the main thing is you've got to check. You must always evaluate the results. So the high resolution modelling can add value, but it won't in every case. So you can't just assume that it's better because it's high resolution. And then on top of that, all of the different data sets give you different results. This is just a few. I've got 5 different sets of modelling data shown here. Don't worry too much about the details, but just look at how tall those bars are. There's a median value in a dark stripe in the middle, and then the tall bar represents the 10th to 90th percentile range in all of the values from those different types of modelling for different seasons. So what do you do with that? You've got some data sets there that are substantially wetter than others. You've got some that are much narrower than others. You've got some that are broader than others. How do you make sense with that? Maybe we should just combine them all like this and just talk about the total range. We don't know yet. So with all of that, it's not enough to just produce a bunch of data and say, here you go. Here it's all available, just knock yourselves out. We have a responsibility to explain how different sources of projections data differ and why they differ, if we can explain that. Why particular emission scenarios have been simulated. Some data that's out there has only been produced for a single emission scenario. Others have been produced for all of the emission scenarios and everything in between. So why were those scenarios selected and what does that mean? What are the strengths and weaknesses of the different approaches? We have different types of regional models. We have different types of statistical models. We have global climate models. They all differ. So what are the differences and what does that mean? Have they all used the same historic reference period when they calculate a change value? Are they all working off the same baseline? And which, if any, of those data sets could you validly use together? Combine their results and actually do something sensible. So the approach we take, and we take this more broadly, but in particular for this project, is we see a difference between projections data sets and climate projections. Anybody who's got a big computer and enough money can produce a projections data set. You just run a model and it spits out a bunch of numbers. But do you believe those numbers, and how much do you believe them, and when is it appropriate to use them and when is it not? And you bring in all of that type of thinking, model evaluation, observed trends, our understanding of climatic processes, all of that comes together into an analysis of what degree of confidence we have in a set of data, We pull that together analytically to produce what we call climate projections. And then you take the projections and you add a whole bunch of value to that to produce a projections package. And that, in this case, projections package includes tailored data sets. We're looking at the full range from as many different types of data as we can get our hands on. We're talking about, okay, you want a subset of data, does it provide the information you need? And work on pulling all of that information together into some plausible climate scenarios for Victoria. So that's what we mean by a projection package. So just to sort of continue on that theme of the difference between data and projections, if we think of all of the results from global climate models, from downscaled models, and all the relevant science, then you can think of it as represented by that big oval up the top. From that information, we can develop our knowledge of plausible regional climate change. And that might be in the form of ranges of change, or it might be qualitative information, but it's informed by those projections data sets. At the same time, we might want to identify a subset of all of those data that we can use in applications. If we think about the total number of global climate models and downscaled models and everything else, it's an enormous amount of data. Very few people can work with that amount of data. So there's nearly always a need to identify a subset of those data to use in applications. That's okay. And they might be in the form of individual models, or they might be scenarios, and they can be developed and filtered for user needs. All of that's fine, provided there's a context for that subset that is defined by our knowledge of plausible regional change, and provided those data sets are representative of our understanding of the plausible regional change. Now, it sounds complicated, and it kind of is, but there are some fairly straightforward ways to cut through that. That's part of the information that will go into the guidance material we'll be producing. So I'm just going to pause here and see if there are any questions, either online or from the room. Where do you want to start?
So there's nothing online yet, but if people who are online want to submit a question through the webinar, feel free to, and we can answer it, get John to answer it in the room. Does anyone who's in the room have a question at the moment?
Yeah, my question is, well, as you say, the models is never perfect. Now, if the model were to produce various situations such as extreme rainfall or fire impact or storm surge or whatever, now when you tune or calibrate the model, do you actually try to get everything about right and therefore everything about not so right, or you try to run your model in different mode to pick up specific?
That's a really good question. But before I answer it, in case you couldn't hear Claire said if you, of the people online, if you have any questions, please use the chat system, the online chat, and send those through. And the question was, correct me if I've misunderstood, that because the models aren't perfect, do we tune models for particular aspects, if you like, such as, for example, extreme rainfall, or not? Or do we run the model multiple times where it's tuned for one aspect and then tweak it and tune it for something else and run it again? Is that essentially, yeah. So what we try to do is to get it to perform as well as it can across multiple measures. And that will mean potentially that you may have to compromise on everything. one of the reasons for doing that is if you were to run the model once optimised for extreme rainfall and then run it again optimised for minimum overnight temperatures and then run it again for sea level, you wouldn't be able to combine those results together in any meaningful way because they would all be running in different worlds, if you like. It would be like different versions of the Earth. And so you've got a bunch of data sets that you wouldn't be able to combine. So if you needed to combine rainfall and temperature to plug into a crop growth model, the data would be meaningless because they're not real world data. So there's a lot of tweaking, refinement that goes on in the model development process. And with global models, there's an international community where the results of model runs are evaluated and that information is fed back to the modelling group that built each model, and they take that information and try and improve the model, and there's a sort of cycle of ongoing improvement. That's also true, but in a smaller kind of way with the regional climate modelling. One difference with CCAM compared to other models is that it's built from the ground up. It's been built to simulate climate, whereas a lot of the high resolution models were from the ground up built to simulate weather. They started as weather forecast systems and evolved into multi-decadal projection systems, whereas CCAM started as a long-term projections tool. And it has a weather mode, but it's fundamentally a climate model as opposed to a weather model. Having said that, because it's an in-house model, we can adjust it whenever we identify that it needs to be adjusted. Whereas a model that's produced by somebody else, you've got to write to them and say, hey, your extreme rainfall's a bit dodgy. And they go, great, okay, well, you know, in 3 years' time, we're planning to work on that again, and we'll keep that in mind. Whereas we can go and I can go and say to Marcus, extreme rainfall. And he goes, oh, let me see, tweak, 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 type. Let's try that again. And so it's a much more dynamic kind of development process, which is great for us. So this version of CCAM that we're running has a different or modified convection scheme. Convection is what defines the rainfall, compared to the version of CCAM that was run for the 2015 national projections that we did. So it's an ever-evolving beast. Yeah.
Could you please explain the difference between statistical models and dynamical? I'm familiar with statistical models and not so.
Okay. So the question was, can I explain the difference between statistical and dynamical models? I'm cheating. So I've just brought up this schematic of a global model, and that's the one on the top right, the big globe. That's an example of a dynamical model. Statistical model is illustrated in the bottom left, and the main, well, for those of you who don't know what a statistical model is, and you can correct me when I get this wrong, statistical models fundamentally look at relationships between broad-scale climate processes and how that translates to what's happening at a smaller scale on the ground. There are different ways of doing this. One, statistical relationships among those different parameters, analog approaches where you look at the broad scale patterns, the synoptic patterns, and you look back through an historic archive and find a synoptic pattern that matches, and then say, okay, well, that's probably what the weather's going to be like at the future time. Whereas a dynamical model runs a computer simulation of all of the physical and chemical processes that happen in the atmosphere. Now, we understand the atmosphere and how it behaves, and the ocean pretty well, have done for a long time. the laws of physics are well understood, the laws of chemistry are well understood, and we're able to, not me, clever people, are able to turn those into mathematical equations which can be solved by computers. That's all fine. You can do that at a point. You could probably do it on a piece of paper if you had long enough. But to simulate the climate of the world, we have to divide the world up into points across the surface and also up into the atmosphere and down into the oceans. So those points translate into grid boxes, three-dimensional spaces. And you can see in this illustration that there's it's like an onion, I suppose, with lots of layers wrapped around the globe, and then you could peel off the oceans as well, and it would go down. About 40 layers in the atmosphere and about 40 layers in the oceans. The dynamical bit is because the supercomputer, because you need a supercomputer to run these things, solves all of the equations at every grid point, up, around, simultaneously, says, okay, that's the situation at this point in time, then steps forward in time by maybe 30 minutes and takes the information from the previous time step, feeds that into the second time step, recomputes everything, and then steps forward again, and does that over and over and over until you end up with 200 or 300 years of data. So it's dynamical in that it's all basically solving the fundamental laws that govern the climate in that kind of way. Now, the strengths and weaknesses to both approaches. Hydrologists, for example, tend to prefer statistical approaches, and they have good reasons for doing that. Probably need to keep moving.
Hopefully we'll have time for questions at the end.
All right. So, skip through to... So what have we done so far? Some of you will have attended the Stakeholder Needs workshop that we ran in November last year. Some of you will have also been involved in additional interviews that took place after that, or may have completed the online survey that we did. All of that information fed into the scoping report, which was then socialised back with participants in the consultation process, and went through a series of reviews within DELP and is now complete. The downscaling work is almost done, and I'll show you a bit more detail in a second. The evaluation of those runs is underway. We've just started. We're also downloading and analysing a new data set that we've not worked with before, which looks at understanding what happens at a regional scale if the planet is at one or other of the Paris Agreement targets. Now, this is an interesting bit of science, because normally when we talk about the future climate of, let's say, 2050, what we're really talking about is a climate that is on its way from what it used to be to what it's going to be way off in the future, and it just happens to be passing through 2050. So it's on its way to a different state. So it's what we call a transient climate. Getting an understanding of what the world might look like when the climate has stabilised is a very different kettle of fish. And this is what this is about. And there was a demand for this from the stakeholders when we consulted, and we saw this as a good opportunity to try this out and see what can be said about Victoria in a 1.5 degree or 2 degree world. We've also started working on the reports, which will emerge at the end of the project, and some fact sheets as well. A bit more detail on those soon. In terms of the CCAM modelling, so the new high resolution modelling work, as you can see, it's almost all done. We're downscaling 6 global climate models. These global climate models are among the 8 model subset that we identified for Australia as part of the Climate Change in Australia projections work. And they were chosen, those 8 models were chosen on the basis of their representativeness in terms of annual and seasonal changes in temperature, rainfall and wind across the whole country. Also, their skill, the model's skill in representing the historic climate, the interrelatedness among these models, which is a big topic, but basically there's 40 odd models around the world and they are all to a greater or lesser extent related in some way. For example, the Australian access model uses the atmospheric component of the UK's model, but we use our own ocean and our own land surface. So it's a bit of a hybrid, and this is fairly common around the world. So these 6 are selected from that 8 model subset. We can't do all 8 because we just don't have time. So we're doing 6, and they all provide the necessary data for CCAM to downscale from. So the first bit is to analyse to complete the historic, which is done. That's a run from 1960 to 2005. So that's running the model to simulate the climate of the past. And remembering this is just over Victoria now. We're not talking about global anymore, although CCAM is global, but at this high resolution we just focused on Victoria. For the low emissions scenario of RCP 4.5, the run is from 2006 to 2100 continuously, and they are all done except for this last one, the NORI SM1M model, which is still grinding away. It takes a long time to do these things. The RCP 8.5 runs, the high emissions runs, are all done. And I should have mentioned this in the background. This project for Victoria is actually leveraging off another project that was already underway for the wine industry in Australia, where they had commissioned equivalent CCAM runs for the high emissions scenario. So that's why they're all complete, because that work started before what is technically speaking the DELP project. And we have those 2 projects. There's an agreement to share all of the data across both projects. So there's a nice bit of leveraging going on. And the post-processing is underway for 5 of the 6 models. We can't start that for NORI SM1 until the runs are complete. What do I mean by post-processing? Well, basically, we've got to do a whole bunch of things to take the very clunky and nerdy data that comes out of the model, turn it into something that is compliant with the international standards, and get it into forms that we can then start to analyse. And in addition to that, there's a process whereby we have to create what are called regional masks that allows us to interrogate these data for the regions of interest for Victoria. And we're doing this for 10 regions across Victoria. And so that's what these masks represent, those 10 regions. These are the regional partnerships regions for Victoria. We have to complete the post-processing, as I mentioned, and prioritise the variables so that we make sure that the most important, what were identified as the most important variables by the stakeholders are completed first. Then there's a process of taking all of those data and uploading them to the research cloud, which makes the data then available to be either served up through Climate Change in Australia or made available to researchers through that research cloud. And then we need to do some additional post-processing to create what we call application-ready data. And essentially those are data that are in a form that are more readily usable than straight model output. What if I just keep going and we take questions at the end of this section? Yeah. So what are we producing? Obviously, we're producing new CCAM model runs. So as I said, there are 6 realisations of this, driven by 6 GCMs. These projections data sets will be at 5 by 5 kilometre grid resolution. So even though I was talking about regional masks, we are also producing the data at this fine scale resolution. So not everything's just going to be smeared out across those regions. and we're doing it for the low and the high emissions pathways. We'll be delivering an evaluation, a detailed evaluation of these new CCAM runs, and that work's actually underway. That map on the right is part of that. Then we'll be comparing the CCAM results with all of the other data that we can get our hands on that are available for Victoria, including the global climate model-based data sets. We'll be post-processing those to produce those application-ready data sets or ready-to-use data sets. That's quite a large body of work, producing those. And as I alluded to before, modelling of Victorian climate under the Paris Agreement targets. In terms of individual variables, data sets that we'll be delivering fall into essentially three categories. The simplest of these is what we call change data. And you can see there's a bunch of variables there for which we'll be delivering change data at annual, seasonal, and daily or sub-daily timescales as gridded data sets and area average data sets where we've computed an average across each of those 10 regions. What do I mean by change data? This is what I mean by change data. If this is the model data from one run of CCAM, say, in blue is the historic run, so the historic world according to this model. In red is the future world according to that model. What we do is we identify a reference baseline to use, an historic reference period that we use as our starting point. We've chosen 1986 to 2005 because that aligns with the IPCC 5th assessment report. It aligns with a lot of the data sets that are currently available for Victoria. It's a lot easier to combine data sets if they all share the same baseline. So it just makes sense to use that one. So what do? We take a 20-year time slice from 1986 to 2005 and we compute the average of this up and down over that 20-year period and we have a value. We then go to our future time period of interest, and this could be any time period you like. I happen to have chosen a time period that would be labelled 2070, but it's actually a 20-year time slice from 2060 to 2079. And again, we calculate the mean of the ups and downs. Then we just simply subtract those two values and we get a change value. And it'll either be a positive or a negative value depending if it's an increase or a decrease. Temperature almost always increases. This is temperature, that's why it's in degrees Celsius. Why do we do this? The reason we do this is because if we were to compare this, particularly the historic run, if we were to compare that with the real world data, there would be a difference. Every model has this and it's called bias. So the model produces a climate that is, in this case, maybe too hot or maybe too cold compared to the real world. But we assume, and worldwide we all do this, we assume that the bias that is exhibited in the historic version of this model will be consistent in the future version. There's no way to test that. It's impossible without a time machine, but it's a reasonable assumption. So if we compute the bias in the historic run, then we understand what the bias is expected to be in the future run. So subtracting these to create a difference like this takes the bias out of the equation. If there was no bias, we would be able to just take the model results as they are. But there is always a bias. Don't let anybody tell you differently. So that's what I mean by change data. So there'll be a bunch of variables made available in that form. Some of the same variables available in ready-to-use forms where we've taken that change signal and we've applied it to real-world observations to produce a bias-corrected, plausible future set of data. And in the case of daily, we can produce a daily time series, for example, which look like real weather, basically. But it's not a forecast, it's just a simulation of a plausible weather-like pattern that's consistent with the expected future climate. And then the third type of data are the raw model data. So for those people who know how to cope with the fact that there's a bias in the data, we make every variable that CCAM produces available. And these will mainly be researchers, because not too many people have the resources to manage these data sets. They're enormous. And if you want to do a computation to remove the bias from something like this, you need a supercomputer, and that's not everybody in the room. So it's a fairly specialised data set, but it's all going to be available. However, by and large, you'll need to come via us to access those data, because it's important that we play a bit of a gatekeeper role, because we don't want people who don't understand that there's a bias in these data to just download them, and then sort of next thing we know, there's a story on the front page of the Herald Sun saying, "Ha, the world's actually cooling. Look, here's CSIRO's latest model data that proves it." So, gatekeepers. Do I sound bitter and twisted? Apart from the data, we are, of course, synthesising all of the information and actually producing what we refer to as projections, where we analyse all of the data, pull it all together with our system understanding and turn it into statements about what future plausible climate is, and convey that through a technical report. Technical report's going to have those contents, basically, the sorts of things you'd expect to see. But I'll look in a bit more detail at the Victoria's Changing Climate section and the guidelines section, because they're pretty key. In the Victoria's Changing Climate section, this is where we talk about the past and future changes in the climate. So we'll be examining temperatures, maximum, minimum, average, rainfall, including extremes, winds, storms and weather systems, relative humidity, evapotranspiration, some narrative drawing on other research. It's not being done as part of this work, it's being done as part of the NEST program on fire weather, narrative on sea level, also from other sources, pulling together the information into some climate scenario statements for Victoria, and an examination of expected changes in some of the climate features that are important for Victoria, like the southern annular mode and blocking highs. And I haven't got a dot point there, but I should have put one about extremes. There will be treatment of extremes in there. In terms of the guidelines, some of the things that we included in the technical report are information around approaches to using climate projections in the impact assessment. It's not straightforward, and people find this difficult, so it's important to put some information in there. Linked to that, there will be an explanation of the CSIRO Climate Futures Framework approach to cutting through the uncertainty space. Information on choosing the right data set for your application, and additional guidance material, which is likely to be in the form of sort of annotated links to other sources, because there's a bunch of information already out there that doesn't need to be reinvented, and some guidance on obtaining climate projections data sets. In addition to that, we've got very strong feedback from stakeholders that they wanted a bunch of other things as well, things that were a bit more targeted at a non-specialist user, particularly things like fact sheets, videos, webinars, and some brochures. These brochures are likely to be very short, but there'll be one for each of the 10 regions, targeted at policymakers. There will also be a training rollout at the end of the project, basically explaining to stakeholders what the new projections say and how to use them, pretty much. A bunch of fact sheets are under consideration at the moment, including things like what to expect from climate projections, because I'm sure if I asked all of you, hey, I'm going to give you some climate projections, tell me what that means, I would get a bit of a range of explanation of what that means. So let's just spell that out, perhaps. But some of the other things that are also covered in the tech report will be covered in fact sheets, like how to use climate projections for impact assessment, how to choose the right data set, things like that. The regional brochures that I mentioned, they will be brief, but they will cover temperature, rainfall and extremes and present key messages about those and try and synthesise what the climate scenarios say for that particular region. They're intended to be easy to read and visually appealing, hopefully with lots of pictures and not too many words. And the webinars and videos will be topic specific, short, and the videos will essentially be recordings of the webinars. And the training, as I said, to key stakeholders, both in the metropolitan area and region. So the last thing to talk about is some preliminary results. We don't have much time, but should probably take some questions if there are any.
I can't see any online. Erin's got one here.
Okay, great.
There was some talk around stakeholders recently who, some people have done the Climate Futures training with CSIRO, and others were wondering if they should wait for the Victorian projections to be released in March 2019 before they do this training in the Victorian context, or whether is there a relationship between the two and should they wait for that timing?
That's a really good question. We don't really envisage running the Climate Futures training as part of the rollout for this project, mainly because it's a 2-day course. And I'm sure our key stakeholders don't want to sit in a room for 3 days because that's what it would take to cover this and the Climate Futures training. I would say don't wait, because we can only deliver the Climate Futures training when we have funding. And we have funding to run a course in September, full stop. So having said all of that, that course is fully booked and there's 60 people on the waiting list. So,
would there be value in rerunning the Climate Futures training once these results are produced, because they could be integrated into the Climate Futures training, or is there not that connection?
there is that connection. So, sorry, I haven't been repeating your question. So the question was, should people wait until these projections are released before doing the Climate Futures training? And I said no. And if once these data are released, if you've done the training, should you redo it? That what you asked?
Or just if there was new training run, would it incorporate the new projections?
Okay, so if there was new training done, would it incorporate the new projections? Well, the answer is yes and no. The Climate Futures training is about this broader question of how do you make sense of all of the data that are available, and how do you identify the most appropriate data for your application? Once the Victorian data are available, there will just be another set of data in the mix for that analysis. So if you've done the training, when the data are available in the Climate Futures tool, they'll just be available and you'll understand how to use them because you've learned the approach. So yeah, not really. So it'll be there. It's just, yeah.
Yeah, thanks.
Yeah.
Okay,
Yeah, okay, sorry. Yeah.
Case from Melbourne Water again. So the question I have then is related to, there's another model or projections coming into the mix.
Yes.
And obviously, as you said, you know, if you go through some Climate Future training, we need to make sense of it. But I wonder this question would be more appropriately answered by CSR or Dell, would be from policy perspective. So, for example, in water supply planning aspect, we already have guidelines, and there's water and climate research ongoing at the same time. And this will throw in another mix. Yes. So what should we do? Or would this, or rather would this project provide, if you like, a link between the group, the Victorian government, to ensure that the user is provided with appropriate guideline, not just using this set of data.
Thank you. Thanks for raising that, because that's a really good point. So Kay has asked, there's existing water guidelines have been developed using statistically downscaled data sets that were developed by the Bureau. There are these new projections that we're pulling together. And at the same time, there's some more hydrological work being done, both by CSIRO, our colleagues in Land and Water, but also Bureau of Meteorology. And they're doing hydrological projections, multi-decadal projections. it's our intention, as far as possible, to write the guidance in such a way as it will guide you to the most appropriate data, no matter what they are. And though there will definitely be links to the Vicky data that underpin the water management guidelines for Victoria, whether there'll be links to the new modelling, I doubt, because our time frames are different. They will still be doing the work when we're finished. And likewise with the Bureau's data sets. But provided we can get those data and put them into Climate Futures framework, then the processes that will be described in the guidance material will still apply to those new data sets. But that, I can't guarantee that those data will be made available through Climate Futures, but it's a possibility. So there will be linkages. As much as possible, we will include the Vicky data in our analysis of where the new projections sit relative to all of the other data sets that are available. So that includes Vicky, that includes also NARCLIM, which is, even though it's New South Wales product, covers all of Victoria. Climate Futures for Tasmania covers the southern half of Victoria. So there's a whole bunch of data, including the Vicky data. So as much as we can, they will be linked, and the guidance material will cover those issues.
I might just add that in the department, we'll also be working with the water area of the department to make sure that when the projections come out, there is some clarity around what should be used. And, you know, we definitely don't intend that these new projections supersede the existing water guidelines for water corporations. So we'll be making sure that those messages are clear.
So I'll just jump into the preliminary results now, and then with a bit of luck we might have time for another question. So what I'm showing now, and note the big disclaimer in the top right corner, I'm sorry I can't share these data with you at the moment. These are results from all of the CCAM runs for 2070, basically, 2060 to 2079, in millimetres per day for, sorry, the CCAM is in the bottom row. I'm really not explaining this very well. The corresponding global climate model that was used to drive climate models that were used to drive CCAM, those 6 are at the top. So you can see the relationship between the host model and the downscale version. And it's showing quite nicely that we're getting enhanced drying in the Alps. So basically these dotted lines here show lines of altitude, lines of elevation, 400 metre intervals. And so this is the southeastern Alps region. So in autumn, winter and spring, we're seeing the same drying signal by and large as is in the global climate models, but the finer resolution is giving us enhanced detail about where that drying is happening. And it's showing that, say, particularly in winter, there's more drying happening at the high elevations than there is at the low elevations. I don't know if you can see it from back there, but there's stippling on these maps as well. And wherever there's a dot, that's the centre of a grid box. And if there's a dot, it means that at least 5 of the 6 models agree on the direction of the change. So where there's a dot, there's a lot of agreement in either drying or wetting, depending on the case. So you can see that for the 3 seasons, autumn, winter and spring, there's a lot of agreement among the 6 models about this signal. In contrast, in summer, it's showing enhanced wetting in parts of the high elevation regions, but there's not so much stippling. There's a bit of stippling in here, which is good, but out here, there's not much. So it's a bit of a mixed bag. In summer, we've got some models saying drying, some models saying wetting. The actual colour that is showing is the mean from all 6. And the means can be misleading, particularly when you've got this situation. There's no stippling, so there's not much agreement among the results. Anyway, as I said, these are still preliminary, although these particular results have been submitted to a journal now for publication. So if that gets accepted, we'll be able to share around the paper. But it's really good news for us because it indicates that the higher resolution is giving us extra information above and beyond what we could get from the global climate models in particular. Another thing is that this also agrees with what's being seen in the Northern Hemisphere. They're also seeing from downscale projections enhanced drying in some seasons in the Alps, and the NARCLIM projections showed similar results for Southeastern Australia, so that's also encouraging. So it does look like we're going to be getting some added value out of the CCAM runs, which is great news. When we started out on this project, we couldn't say whether or not we would get added value out of the high resolution modelling. And that makes people spending money nervous. So this is good. This is the same results, just in terms of percentage change. So here we've computed, in the same way as I explained before, for that change signal, we've computed the difference between the historic and the future and represented that as a percentage change. And it's informative because if there's something really strange going on in the model, you might see a different result when you compute it as a percentage change in terms of the patterns, and the patterns are essentially the same. So that's really, really encouraging. Really quickly, I mentioned that we'd started doing some work on what Victoria might look like in a Paris Agreement target world. In this particular case, we're looking at data for a 2-degree world. And you can see that for temperature, mean annual temperature, by end of century, you can see that the temperature traces stabilised a little bit. Oops, sorry, started to level out here. And you can see that that's slightly less than 2 degrees, which is kind of good news for us. The world on average is 2 degrees, we might be a bit less. But look at the range. So we've got 11 simulations here, and there's a big lot of variation there going on. So anyway, it's interesting. Very early days. We haven't really done any evaluation of this yet. We've also started to look at long-term projections for Victoria. We normally deal with projections out to 2100, and most people think that's pretty long-term. We don't. For us, long-term is like 1,000-year runs, but these are kind of, middling along out to 2300, and just having a bit of a look at what is happening with annual temperature under 3 different emissions scenarios and cool season rainfall for Victoria under, this blue line is kind of RCP 4.5 and 2.6 combined. I don't understand that, so don't ask me questions about it. But it's interesting to see how these trends are expected to continue beyond 2100, but depending on the pathway that we follow, of course. The green one's nice. That's coming back down in temperature. That'd be really nice. And really long-term changes going back to the year 1000. There's a reconstruction of summer temperature for Victoria. Well, it's actually for I think it's for Southeastern Australia. Oh no, it says Victoria. So you can see a reconstruction, I hope you can see it, in grey, this sort of squiggle that's really lots of ups and downs, but very stable for 1,000 years, just about. This black line over here, the really dark black, is actually observations, a data set called Acorn Sat, which is built from observations, and then the projections for 3 emissions pathways. What a difference compared to this very long-term historic temperature to where we could go in the future. Again, we haven't analysed these or evaluated them in any way, but we're just starting to work on this. So, fundamentally, what we're trying to do is, as well as producing some really good science, take all the information and make it understandable to the end users. With a bit of luck, we'll get there. Thanks very much. We are over time.
We are. If people are able to stay, we can take some questions, and we'll keep running the webinar. Okay. So if people are able to stay, we can take a few questions, and we'll keep running the webinar while we do that. If anyone has to leave, we have our afternoon tea outside, so please grab some on your way out. But we'll see if there's any questions. Are there any questions for people in the room?
How are you getting the afternoon tea to the people online?
Carrier pigeon?
Yeah.
When the sixth assessment report comes out, will this need to be refreshed?
When the sixth assessment report comes out, will this need to be refreshed? That's actually not a science question. It's a user expectation political question, because scientifically, no. There's nothing wrong with the projections from CMIP 3, so from the fourth assessment report. There's no major differences in what the earlier projections said compared to the most recent projections. What did get improved is the availability of data. So with the CMIP 5 or the fifth assessment report results, all of the modelling groups around the world were able to produce a more substantial set of data that's available to us, that we can then make available to end users. So that's part of the story. So, for example, New South Wales did the NARCLIM projections work, which is a high-resolution modelling effort focused on New South Wales, but it comes across Victoria as well. They used the older model data, the CMIP 3 data. There's actually quite compelling scientific reasons for doing that. At the time, the CMIP 5 data were brand new, and in fact, not all of the data we had available. But they could have decided to run with what was available and choose some models from there to downscale and run with that. But then they would have been dealing with the brand new data that really nobody had much of a chance to have a good look at and do some analyses of. By using the CMIP 3 data, the older stuff, there's a wealth of published material about the strengths and weaknesses of those modelling efforts, which they could then use to inform their model choice and their interpretation of the results. So it was actually a pretty smart thing to do. But they have got pushback from their users. They've now got all the users saying, when are you going to give us CMIP 5 versions of those projections? So it's fundamentally about how applicable people see the results, and people think the latest must be better. So there's a real push to get the new stuff. And yes, there are some reasons why new can be better, but overall, there's usually not a lot of difference. So with CMIP 6, there will be more models. That probably means there will be at least as many variables available, if not a few more. There's going to be more of an effort on the Paris Agreement targets. So there will absolutely be new stuff that you can't get from the old, but we're having a crack at that for Victoria anyway. What else is going to change? There's going to be a bit of effort on compound events, where you have multiple extreme events occurring together. That work started, so that will be different from anything that's come before. But from the point of view of just projections of temperature and rainfall and probably extremes, there's not much likely to change that much. Yeah. But we'll see. The other thing is that... No, that's all right. I'll stop talking. I think up the back.
I just wanted to know about the grid itself. You put it over Victoria to be most accurate. How far outside of Victoria can we go? We're from parts of Victoria, and I guess we're kind of interested to see what's coming our way, if temperature changes, or what's going to be in our parks in 50 years or so. So how far can we go out into the ocean, into New South Wales, to South Australia, and be confident that the grid's still accurate?
Okay. Because I think what you're asking is, because the grid is stretched and it's smaller at the core area of interest and then it gradually gets bigger as you go further away, how far can you go and still get reliable information? Notice I didn't say accurate. Accurate and the future, they don't go together. So the grid very slowly grows. It is 5 kilometres by 5 kilometres over all of Victoria. I'm not actually sure what it would be at Dubbo, but it wouldn't be as big as 50 Ks. It would probably be Dubbo, I don't know, I wish Marcus was here, maybe 10 Ks, 10 or 15 Ks. But if you looked at Paris, it's probably going to be 500 Ks. So the actual climate that is being simulated in those grids is still fine. There's nothing wrong with it in terms of the robustness of the modelling. It's purely this spatial scale that changes. And so, of course, once you get to a 20K grid, it's able to simulate less of the fine scale processes than at 5Ks. But it has to be said that even at 5Ks, there's quite a lot of important processes that aren't directly simulated. They still have to be parameterized, because if you've got a convective system that is less than 5 kilometers big, it's not going to be dynamically generated. Ideally, we'd be doing it at 1K. Can we go for another 5 years? And yeah.
Yeah, hi, my name's Dominique. I'm here from South East Council's Climate Change Alliance. My question is probably a bit more for Del, if I can.
Cool.
Because amazing science, can't wait to see it all, like it's fantastic data. My question is, what are we going to be doing about taking this marvellous work and having it taken up by those who are developing, regulating the planning system? What are we going to do about the fact, for example, that in the Local Government Act there's going to be a requirement, or the proposal is for a requirement for councils to consider climate risk. This is exactly the kind of information they need to enable them then to do their jobs. So I take all the science, I think it's absolutely amazing, but the really big challenge is then to actually make it able to be utilised and to change the way we're planning.
Yeah, so for anyone on the webinar, the question was about how the data that we're getting out of this project is going to be incorporated into, say, planning scheme and regulations, so that councils and others need to take it on board. And through the process, through the scoping, we've been working with different areas across government, including planning, to work out what needs are and how it can best, what existing systems people have for it to be incorporated into. So we'll be continuing that throughout the process and continuing to work with people. There's a big push from the climate change area of government for climate change to be mainstreamed across government. So that this will be, I guess, one of the tools that will be considered throughout that process. But yeah, it's a really good point.
Just on that, one of the headings in the table of contents of the technical report that I didn't talk about is the policy implications. Policy, I forget the actual wording, but it's about policy. It's where we will, it won't be a very detailed section, but it will be talking a little bit about what the projections can contribute in the policy setting, so that might at least be a bit helpful to government from that perspective. I think, Caius, did you have a question?
Yes, I do. It will be a short one. So it's AR now. How do you tie that in? Or sort of leverage how AR could leverage this?
Yeah.
And how do you tie it?
Yeah. So the question was how does the new work relate to the Australian Rainfall Runoff Handbook? Can they be interconnected in some way? So yes and no. The Australian Rainfall and Runoff Handbook will presumably be revised at some future time. It's developed by, I think it's Engineers Australia, is that right? The head body that does that. We did some modelling work for the last revision of the handbook and attempted to address the question of what is expected to happen to short duration, high intensity rainfall events, which are crucial to design of drainage systems. It's a really, really curly problem, very difficult to solve, and we were unable to actually simulate those timescales in any way that we felt was robust. So instead, sort of took a step back and said, all right, well, probably the best guidance is just to work with what's called the Clausius-Clapeyron relationship, which says that for every degree of heating of the planet, so mean global warming, for every degree, expect a sort of 5 to 7% increase in the intensity of extreme rainfall events. It's a very blunt instrument, but it's better than not having any climate change factor, if you like, in those design standards. So in the next version of the handbook, we will be hopeful that we will be able to do some more modelling, but it won't be the modelling that we've done for this project because it's not fine scale enough. It has to be done at 1 kilometre or 2 kilometres to be able to inform those questions. 5 k's is just too big. So that means that you couldn't do it in any sensible way for the whole of the country, and even just to do the whole of Victoria at 1 kilometre resolution would be very expensive and time consuming. So what they did for the work that was done for the last version of the AR&R handbook, they just focused on Sydney and Melbourne and did some 1 kilometre resolution CCAM runs for Sydney and Melbourne. And it will probably be a similar approach again next time, I would guess, but I'm only guessing. So we will try and make whatever connections we can with the AR&R, with our analysis of the extreme rainfall, but it will be limited because of that scale question. We certainly can't produce, new future intensity, frequency, duration curves or anything like that. But our colleagues in Land and Water and colleagues in DELP, I think, are working on these problems. So hopefully there'll be additional information that will come from this 5K modelling that will help with that process, as well as the new statistical modelling that is being done by Land and Water, Land and Water. So we're not actually doing any hydrological projections as part of this work because it's not our field of expertise mainly. And what we're doing is we're talking with the hydrologists at SARO and DELP to try and make sure that the data sets we do develop and provide are as suitable as they can be for their work so that they can take it and value add in those projections. Is that a good question?
We've got one online as well.
Okay.
Did you have a question?
Did you have a question?
I did have a technical question about that bias calculation. Is that a standard approach? Is that ambitious? Because when I saw that the period from 86 to 2005, my first thought was, but that includes the millennium drought.
In the real world, yes.
For Australia. Does that impact on the bias calculation model, right, or does it not matter?
Okay. So the question was with the change, so it's called a time slice change method, and when we calculate that change signal to remove the bias, is there an issue if, for example, that period of time over which the historic reference period is taken contains something like the millennium drought? The first thing is that the historic period is the world according to the model. It's not the real world. That means that even if the model simulates droughts like the millennium drought, they won't be at the same time as the millennium drought unless by just complete chance. The models don't attempt to simulate the historic climate and get it right year for year. Because they're global climate models, they simulate mean climate state. And so those types of big changes, even though the millennium drought was a really big drought, it's still fundamentally a natural process. It's an example of natural variation, natural variability. And what we're looking for from global models is for them to simulate that natural variability in terms of the statistics and get those roughly right, but it won't get the timing right, and that's not expected. So there could, by chance though, be a millennium drought in that 20-year time slice. And if that's the case, yes, it will have a bearing on the calculation of that change. The only way you can check for that is to actually look at a time series plot like the one I showed, where you would hopefully see that, oh, hang on, right in our reference period there's a massive dry spell, maybe it's not a representative measure. But by and large, the global climate models don't simulate those types of drought events. They can be made to do so when you do specialised research, but in those generic runs for the whole globe, they don't tend to pick those things up. So we have confidence that the 20-year time period is a reasonable enough time slice to use for those calculations because of the lack of, because it's model world, not real world fundamentally. So the nature of the variability signal, although it's similar to the real world, it's not quite as variable as the real world. I don't think I've actually answered your question, but we can talk about it a bit more offline. But related to that is when we've taken real world observed data sets to produce future versions of plausible weather-like data for the future, then we do very much take into consideration, has there been anything happening in that 30-year time, or in that time period that we want to use, has there been something happening that we do or don't want to include? Is it going to be unrepresentative of the mean state of the climate? So for the climate change in Australia work that we did, we were going to do a 20-year time period and scale that to produce future data sets until we realised that that was going to have the millennium drought in it. So we extended it to 30 years so that we tended to smooth that out a bit. So yes, the millennium drought is in that data period, but it's also got 10 years at least of non-millennium drought, 10 to 15 years of non-millennium drought in it too. So it tends to smooth that out a bit. So it's far more important with that process than it is with the actual model change calculation. There's always the fundamental risk that when you calculate that change signal, just by chance, the model will be in a dry or wet phase or a hot or a cool phase, and that will affect the result. There's no doubt about that, because you have both natural variability, or at least the model's version of natural variability, happening at the same time as the climate change signal. So that is a shortcoming of this time slice method. There are other approaches that don't suffer from that problem, but they suffer from other problems. And on balance, the time slice methods are probably more robust. This is one of the reasons, one of many reasons why we say always look at the full range in the projections data sets before you start making decisions about which results to use. Because if one of them's got this problem, they won't all have. Very long way to answer a really simple question, sorry.
All right, so we might make the last question from online, make that the last one, just given we're quite over time already. This one's a question from Jane Fisher, who asks about the 2-degree increase in average maximum temperatures for summer and how that relates to RCP 8.5 predictions of 4.83 degrees and what's being observed in terms of increases in extremes of temperature.
I'd like to read that. Prediction of 2 degrees increase in average maximum temperature for summer. So is that from the 2-degree world? I have to bring that slide up. I did say those results are preliminary. So, this one. Okay. Jane, can you just tell us which predictions you're talking about?
From the 2-degree world.
So it's not maximum temperature, it's annual, it's mean temperature. So a 2-degree world, I'm sorry, Jane, I'm not 100% sure I've understood your question, so I may not answer what you want to know. And it's not a summer temperature either, it's an annual. So am I looking at the right plot? I don't think I put any summer temperatures unless it was the CCAM results. Oh, this one. Summer temperature anomaly, 1951 to 2000. No, that's not it either.
So Jane's just replied that we'll talk offline.
Yeah, we might have to talk offline because I don't quite understand the question. Maybe I'm just being really dumb, which is quite possible. But a 2-degree world is a long way from an RCP 8.5 world. A very long way. So.
All right. Thank you very much for that, John. We might close it there. Give John a round of applause. So it was really good to be able to get and to share an update on the project and where it's at and what you can expect towards the end of it. Feel free to definitely keep in touch. I hope you all have my contact details. Very happy to chat anytime over the next few months, I guess, while we wait for products coming out of the project. And if you have any questions, you're welcome to hang around now and ask them directly. Feel free to grab some afternoon tea on the way out in the foyer area. And thank you once again.